Hello everyone. There's two topics left to cover, parametric equations and polar coordinates. So these are what I'm calling the final exam topics. You won't be tested on these prior to the final exam, so it's important to make sure that you're comfortable with this material. And in the final exam new material folder in Blackboard, I've posted the final exam topics document, and I broke this down by topic, name, and gave you reference questions. Remember, you can bring the table with the test for series and write anything that you want on the back. The only rule is that it has to be handwritten, and use that on the final exam. You're on your honor. I'll have you sign an academic integrity form to hopefully ensure that you'll follow the rules and treat this as a proctored final exam. But I've broken it down for you into three parts. Part one, you can see, is derivatives and integration. Only study the questions that I've referenced. You won't be tested on every single topic. So I've made things a little bit simpler, like, for example, concerning the integration by parts questions. You just have a single use, and that would be Exam 2, Question 5A. All the exam solutions are posted in Blackboard. And integration by parts, the tabular method. So you got two examples to look at there. So I would say, in terms of preparing for the final, go through these problems, review them, maybe just try them over again. Chances are you won't remember exactly solving them, and that'll be good preparation for the exam. But the point of showing you this now is that the two topics, parametric equations and polar coordinates, are in part 3. There's no reference questions, but I will have a summary for you of these two topics once we're finished covering them. But you can see the types of questions that I'm going to ask there, and there's reference problems for homework posted in Blackboard, and there's for the parametric equation homework, and then there's an assignment here for Mr. Brown's book concerning the polar coordinate work. So getting into parametric equations, we first define a plane curve, or just simply a curve, by a set of ordered pairs, but instead of saying x and y, we say f of t and g of t. And you'll see this often in mathematics. They'll state in a definition or a theorem where the functions are continuous on I. I is just some interval. And so then a second definition is, let C be a curve, defined by the previous definition. And we state that the equations x equals x of t, or you could say x equals f of t if you like. Maybe I should have stated that. And y equals g of t. These are the parametric equations with a parameter of t. So although I'm not going to ask you to sketch a set of parametric equations, I think it's kind of important to see an example. And, if we have nothing, if we have to graph something and we don't know what it looks like, we'll set up a table of values. But now, because we have this parameter t, the table of values of x and y are going to be determined by these values of t. So we'll set up a 3-column table here. T, x is 2t in this example, and y is t squared minus 1. Okay, so we're given a range for t. We'll start at -1. If we plug a -1 in for t here, we get 2 times -1, or x is -2. Plug a -1 in for t into y, we get -1 squared is +1, minus 1 is 0. Okay, to get a more accurate graph, instead of just jumping right to 0, I'm going to go to -1/2. If I plug a negative 1.5 in here for t, we get 2 times negative 1/2 or negative 1 for x. Plug a negative 1/2 in here. Let me go up to the top here. Negative 1/2 squared minus 1. That'd be 1/4 minus 1. Or negative 3/4. So that's our value of y. So make sure you know, obviously, where I'm getting these numbers from. Okay, now we'll go to 0. When t is 0, x is 2 times 0 or 0. When t is 0, y is 0 squared minus 1 or negative 1. Okay, I'll go to 1/2. 1/2 is going to be, let's see, 2 times 1/2 is positive 1. But for the y, it's going to be the same as the negative 1/2. Because if you put a positive 1/2 in here, it still is 1/4 minus 1. Or negative 3/4. Okay, let's go to 1. When t is 1, x is 2 times 1 or 2. And when t is 1, 1 squared minus 1 is 0. I'll go to 3/2. And maybe doing the work up top. 3/2 squared minus 1. Oh, this is for y. For x is just 2 times 3/2, which would be 3. Excuse me. And for y, it's 3/2 minus 1, or 9/4 minus 1, which is 5/4. And finally, when x is 2, or excuse me, when t is 2, x is 2 times 2 or 4. And y is 2 squared is 4 minus 1 or 3. Okay, so let's make a sketch out of this. We're in the xy plane. And let's see, x ranges from negative 2 to 4. And y ranges from, looks like negative 1 to 3. Alright, so then just plot the points. The xy coordinates, negative 2, 0, that's right here. Negative 1, negative 3/4, roughly here. 0, negative 1, right there. 1, negative 3/4, roughly here. 2, 0, definitely right there. 3, 5/4, approximately here. And 4 and 3 around there. And so then we could join those points. And we get a graph of what looks like, if we extended it in both directions, certainly looks like a parabola, right? Now, the significance of the parametric equations, because you might be saying, why don't you just sketch a parabola? It indicates the motion. A lot of times in physics, you'll see questions that read, a particle moves along a path defined by, and then they'll give the parametric equations for x in terms of t and y in terms of t. So the significance of this is that we could actually use arrowheads to indicate, let's say, the direction of the movement of the particle. So, for example, as t increased, okay, we went along this path here. So you could actually use arrowheads to indicate that. And that's significant in many applications where, maybe it was moving in the opposite direction along that path. So that's how we could sketch them if we needed to. Before we get into a method that we call eliminating the parameter to be able to actually identify, transform this pair of parametric equations into a single equation in terms of x and y, and then identify the graph, just wanted to remind you of conic sections and their equations. So recall a general conic section. A conic section comes from a double napped cone. So you have a cone on top of a cone. And you slice the cone with a plane, a two-dimensional surface. And then you generate these, what we call the conic shapes. And so we're all familiar with the straight line. That would be if we sliced it along the diagonal. And pay attention to the degrees of x and y. That basically dictates the type of graph that we have. To get a parabola, if you slice this, let's say vertical, well, not vertical, but let's say you slice it along a little corner here. That gives you the image of a parabola on your two-dimensional plane. And so it could be either concave up, vertical axis of symmetry, or concave up or down, depending on A. And notice that y is first degree, x is second degree, or open to the left, open to the right. So this is obviously just a straight line. This is either concave up or concave down. Okay, this is when you switch x and y. That's either open to the left or open to the right. Still a parabola. Here's a circle. Slice it parallel with the base. And you can see, using your spatial senses, you get a circle. And slice it, let's say, along not parallel to the base, but just through one piece of the cone. You get the ellipse. And then slice the hyperbola, slice it perpendicular to the base, and you get two parabolas. So let's say a parabola here, and then one down here. And that's the hyperbola. And I guess I could have given two equations for the hyperbola, either where its transverse axis is vertical or the transverse axis is horizontal. Now you don't have to really worry about graphing or anything like that. All you have to do is be able to identify them. And notice the degrees. If it's linear, x and y both first power. Parabola, one of them is first power, one is second power, depending on if it's up, down, left, or right. Circle, both are squared, coefficients are equal. Ellipse, both are squared. It's a sum of two squares, just like a circle, but the coefficients are not equal. And a hyperbola, both are squared, but it's a difference. So be able to recognize the graphs as you should from past experiences. And now we get into the process we call eliminating the parameter. It's a little method here that we use to determine the graphs based on the equations. And so, as I mentioned earlier, this method requires us to transform a pair of parametric equations, so x equaling f of t and y equaling g of t. So a pair of parametric equations in terms of a single equation in terms of just x and y. So essentially we're eliminating the parameter t. Hence the name, eliminating the parameter. Okay, so there's two strategies. Solve one, if it's algebraic in nature, we're going to solve one equation for t and substitute in the other. But if there's sines and cosines involved, which there typically are, so I'll just say this is trigonometric in nature, then we're going to solve for sine of t and cosine of t respectively, and then substitute into the Pythagorean Theorem, because that's a known relationship. I'm getting a little lapse here in the video. Okay, so first example, eliminate the parameter and identify the graph. So look for the easier one to solve for t. And in this case, it looks like x, because x is linear, y is quadratic. So we're going to solve this for t. So if x is equal to 2t, t is x over 2. And then we're going to substitute it, that expression for t, into the other equation. So y equals t squared minus 1 becomes y equals t is x over 2, quantity squared minus 1. That would be x squared over 4, or I'll write 1/4 x squared minus 1. And then by inspection, that's in standard form for a parabola. And so that's all I care about. Get the standard form for the equation. Tell me what type of graph it is. If you wanted to go further, you could say concave upward, because its y is in terms of x squared and the coefficient is positive. Okay, here's the second equation. Oh, and notice that that was actually our example that we sketched, right? So that proves, so go back and check that out. That proves that our graph was correct. It is actually a parabola. We've just proven it by this method. Okay, then in this case, second example, again, pick one that's easier to work with and solve for t. Looks like x again. Y just takes an extra step, but I'm going to choose to go for x. Doesn't matter, it's going to work out either way. Okay, so I'm going to solve for t here. Add 2 to both sides. X plus 2 equals t. Take that and substitute. And y is 2t plus 3. So y would be 2 times t now, x plus 2. Don't forget plus the 3. Obtain a standard form, distribute the 2. We get 2x plus 4 plus 3. And y equals 2x plus 7 is our standard form for the equation of a straight line. Okay, in example 3 here, again, look for the easier one to work with. And because x is quadratic and y is linear, looks like it's going to be easier to solve y for t this time. Okay, so y is 2t plus 3. First transpose the 3. So y minus 3 is 2t. Then divide by 2. So y minus 3 over 2 is t. And then we're going to substitute into the other. And x was 4. Let me rewrite it before I substitute. So x is 4t squared minus 5. So x is 4, t, y minus 3 over 2, quantity squared minus 5. Again, try to obtain a standard form. Here I'm going to take it a little bit slowly. So you have x equals 4. I'm going to square the numerator, but not literally yet. Square the 2 to get 4 in the denominator. Then the 4's will cancel. So we get x equals y minus 3 quantity squared minus 5. And that's actually recognizable right away as a parabola. But if you want to, that's what we call the vertex form for a parabola. But if you wanted to square the y minus 3, so you get y squared minus 6y, FOIL it out if you need to, plus 9, and then don't forget the minus 5 that's tagging along. And so we get x equals y squared minus 6y plus 4. And then we can see that it is a parabola. It's going to be open to the right, but just tell me it's a parabola and I'm good with that. Alright? Okay, here's a trigonometric equation. So those are examples of the algebraic types. Here's the trig functions. So we're going to solve each one for sine and cosine respectively. So x over 3 is cosine t, and y over 3 is sine of t. And then we substitute, but what we're substituting into is sine squared t plus cosine squared t is 1. So that's a known relationship. And so we have equals here. Sine of t is y over 3. That has to be squared. Cosine of t, x over 3. That has to be squared. So y squared over 9 plus x squared over 9 equals 1. And now because the coefficients are the same, let's multiply everything by 9. I want to show that. And distribute that y squared plus x squared equals 9. And if you want, put the x squared first. And then you should easily identify that as a circle. Okay, as opposed to the next example, where we have x is 5 sine t and y is 4 cosine t. So, same procedure. Solve for cosine t, we get x over 5, or solve for sine of t, that is. We get x over 5 is sine of t. Solve for cosine t, y over 4, cosine of t. And substitute. And so again, we're substituting into sine squared t plus cosine squared t is 1. And sine of t is x over 5. But that has to be squared. Plus cosine of t, y over 4. That has to be squared, equaling 1. So we get x squared over 25 plus y squared over 16 is 1. And now because the coefficients, in this case the denominators, are not equal, then we'll leave it in that form because that's the standard form for an ellipse, sum of two squares. Okay, next example. And so, well, you're going to have two questions. If you look at the final exam topic sheet, it mentioned you're going to have two questions on eliminating the parameter. 6 points apiece worth 12 points. So, excuse me, you can guarantee one of the questions will be the algebraic type and one the trigonometric type. So here's a couple more trig types just to finish this off. Again, solve for cosine and sine respectively. Oops, there's a typo here. Let's see, let's change this to 2 sine of t. Okay, so make sure you make that change, otherwise it's not going to work. Okay, and so we'll solve that one for sine. So x minus 7 equals 2 sine of t. So first transpose the 7, then divide by 2. And then for the equation involving y, first transpose the 6. So y minus 6 equals 2 cosine t, and divide by 2. So y minus 6 over 2 is cosine t. Then we substitute again, and we'll go into the Pythagorean Theorem. Sine squared t plus cosine squared t is 1. So sine is the quantity x minus 7 over 2, but that has to be squared, plus cosine quantity y minus 6 over 2, but that has to be squared, and that's equal to 1. Okay, I'm going to take this a little slow. I'm just going to say x minus 7 quantity squared over 4, plus y minus 6 quantity squared over 4 equals 1. And then noting that the denominators are the same, I'm going to clear the fractions. See, if the coefficients are the same, it's a circle. So when we get standard form by multiplying everything by 4, so we get x minus 7 quantity squared plus y minus 6 quantity squared equals 4, and that's a circle. And if you want to go further, you can identify the radius in the center, but that's all I'm caring about, is that you eliminate the parameter and tell me what type of graph it is. Alright, and final example for this idea. So I think I've covered almost all the different cases. Again, sines and cosines involved. So solve for sines and cosines respectively. First transpose the 4, very similar to the last example. So x minus 4 is 3 sine of t, divide by 3, x minus 4 over 3. So sine of t, do the same thing for y, transpose the 5. Y minus 5 is 7 cosine t, divide by 7, y minus 5 over 7. Cosine t, substitute, and again we're substituting into Pythagorean. Sine squared plus cosine squared is 1, so sine is x minus 4 over 3, that has to be squared, plus cosine y minus 5 over 7, that has to be squared, and that's equal to 1. Again, I'm just going to square the numerator, leave it as a binomial squared, square the denominator, 3 squared is 9. Similarly here, y minus 5 binomial squared, 7 squared 49 equals 1. Now since these denominators are different, then we know that it's an ellipse, and we'll leave it that way because that's standard form. Okay, so that's eliminating the parameter. We'll come back in the next part and do some calculus with parametric equations.